All right, welcome to kind of our pre-lab lecture here for the second part of chapter 2, or really the first part from the textbook. But we're going to be taking a look at atomic structure, a little bit of theory that kind of goes with it, and some background. Some of it will be a little bit kind of history-based, which we probably won't really review much in class, but we will kind of hit highlights of this as we talk about these kind of topics in lecture. And hopefully we'll see more examples of kind of what things do we really want to know and be able to take away from a lot of this information. So as a starting point, I want to talk about kind of just like really, how did we get to where some of our current thoughts are on atomic structure in terms of the way we talk about and understand atoms and kind of what makes up atoms, and how that's useful to us in chemistry and kind of understanding some of the things we're going to be doing in future chapters. And so really, remember kind of going back to our first day of class, one of the main questions that scientists, particularly chemists, are always asking themselves is what's the world made of? Right? So once kind of scientists got this idea that we can break things down to atoms and everything that we make from kind of a almost chemical perspective in terms of the composition of things, we can break down into like the individual elements involved and its atoms of those individual elements. Well, naturally, just the next progression of that question is what makes up atoms, like what's beyond that. And so that's what we kind of take a look at here. And the idea of having kind of these building blocks of matter, that it's these kind of small particles being built up over and over and over again to, make large scale like materials or things that we can like visibly see or hold in our hands, really has been around for a long time. Uh, all the way back, dating really to ancient Greece, the idea of the atom has kind of existed. That there's always got to be some kind of like piece that is kind of the fundamental building block, and that's actually when we talk about atoms, it actually comes from the Greek word atomos, uh, which really represents kind of the fundamental building block when we're talking about kind of building materials or putting things together. And that's kind of what we're going to be looking at a lot here today is not just like, what comprises the atom and kind of what's beyond that. Just because the atom can be broken down, the atom is really still our fundamental building block because that's what we can associate to elements and the way we kind of understand chemistry really today. 100 years from now could look totally different in how we view all of this stuff. But for right now, that's kind of how we view things. We talk about elements and kind of what elements are involved in compounds, and we can talk about like how many of them there are and what the ratios are, and that actually kind of gets us into our next piece here with Lavoisier's laws, uh, understanding kind of you know all of our chemical reactions that we talk about involve the elements interacting with each other, not the atoms themselves really being changed, which is something we will see a little bit here before we kind of really move on to chapter 3. We will talk a little about nuclear decay reactions in kind of the next lecture, which will actually look a little bit at if you have atoms and try to break apart the atoms, what happens. So that'll be a little bit different too. But coming kind of back to, like I mentioned here, with these Lavoisier laws and looking at kind of the composition of compounds and the understanding of kind of where this all kind of started and came from when we talk about chemistry. Antoine Lavoisier, kind of in the late 1700s, is often credited with kind of really beginning kind of the study of what we now kind of consider chemistry in a lot of ways, with some of his findings regarding chemical compounds. He proposed a few different laws. One of the most common ones that you'll see pop up kind of over and over and over again is this idea of conservation of mass, which is basically that if you're doing a chemical reaction, you can't create or destroy mass. So your total mass of everything that you start with should equal the total mass of everything that you end with, as long as you can track it all. Sometimes it can be deceiving, like for instance, if you react two solids and one of the product's a gas, if you don't have a way to trap and mass the gas, then it might look like the mass is changing. But in reality, if you could trap the gas and mass it as well, which there are ways to experimentally do that, then you can actually see that the mass is conserved for chemical reactions that way. And something to kind of keep in mind with this, that doesn't mean that when you do a reaction, whatever the mass of your reactants are initially is going to be the mass of the products. It doesn't actually, and I guess I should be careful about how I kind of maybe phrase this, like the total mass of everything at the beginning should equal the total mass at the end. But when a reaction is kind of reached an end point, it doesn't necessarily mean that all your reactants are now products. And we'll be looking at some things that can affect this kind of throughout the general chemistry sequence. We'll talk about stoichiometry in the next chapter, or next couple chapters really, and the fact that just because you have lots of reactants, if they're not in proper ratios to each other, one of them might just be in huge excess, and you might just have a bunch of leftover reactant at the end of the reaction. So how kind of this conservation of mass works is like the total amount of reactants you start with should equal the total amount of both reactants and products that are going to be left at the end of your reaction. And that's kind of the clarification point that I wanted to kind of add in there that you see kind of here in the notes. Some other things that Antoine Lavoisier kind of proposed that are also kind of important to chemistry in general. One is the law of definite proportions, which sounds probably a lot more complicated than it really is. But basically, it states that any particular compound will always have the exact same ratio for the elements that make it. That's kind of how I interpret this. And so a way to think about this from like a chemical formula standpoint, since we've been doing a lot of naming and looking at chemical formulas, uh, when we talk about water, water is always H2O. It'll never be H3O. It'll never be H2O2. Those are different compounds. And so that idea that like for one particular compound or substance, its ratio of its elements will always be exactly the same is actually a pretty impressive thing to have been discovered this long ago, in terms of kind of understanding kind of what things really are comprised of, all the way back in the 1700s when there really wasn't a lot of technology to kind of aid in looking at that stuff. But it is something that's important, obviously, because like I mentioned water as a general example, like water is something we all need to survive. But if we change the ratio of those elements to H2O2, hydrogen peroxide is something that if you drink in a high concentration, probably could kill you. So very, very big difference in terms of changing those ratios for what happens to those compounds and those substances, and they're very important. And it's important to understand that the ratio of the elements involved does play such a critical role into those compounds and what their properties are. And that's kind of the example I give here, kind of supporting his. You can also, rather than just looking at the ratio of like the elements themselves, you can think about it as a mass ratio, which eventually, then as we talk more about the idea of atoms, will then give us like the chemical formulas of like H2O and things like that. And eventually, kind of as time moved along, like scientists were kind of putting together these ideas, like the thought and the idea of the atom back in ancient Greece, like kind of trying to start understanding like how compounds are put together in the late 1700s, Lavoisier. But it was really John Dalton in the early 1800s that first proposed what we now refer to as atomic theory, which had four kind of really key ideas, most of which are still relevant today. A couple of which we'll talk about are maybe a little outdated. And this basically just kind of comprised all of the previous ideas that people had, and started kind of collecting them in one spot in a way. And so his major ideas were that matter itself can't be broken down really beyond atoms. This is kind of our building block piece. And again, atoms themselves have pieces to them, but atoms kind of are the actual fundamental building block of everything, in terms of kind of understanding chemistry and the chemical reactions that take place. Additionally, the different types of atoms that we call elements are characterized by their mass. Now, this is the part that has changed a little bit. Atoms of the same element he proposed at the time have the same mass, and atoms of different elements have different masses. This isn't, and I think that maybe the catch here is if you look at the periodic table, all elements have different masses. But as we talk more in this chapter about where those atomic masses actually come from on the periodic table, we will see some things that it's not quite this easy. There is something called isotopes of different elements, so atoms of the same element actually can have slightly different masses, and that's why all the masses that we see in the periodic table aren't always whole numbers, because they're really kind of what we call a weighted average. So it is possible to get two atoms of different elements that actually do have the same mass, but for the most part, if you're working in a lab, you're never going to be working with just individual atoms. You're working with kind of large quantities of them. So really, if you're taking into account kind of that from that perspective, the average mass of a particular element will always be different in terms of like the mass of those atoms. So like if you have a whole pile of oxygen atoms, its mass can be very different. If you have the same number of atoms of, say, carbon, they'll have very different masses as a result. So you can still differentiate this way, but I do want people to understand it's not individual atoms that this necessarily applies to. And as we talk a little bit more in this chapter, we'll see that the individual elements are actually characterized by the number of protons specifically, rather than just the actual mass, although they are kind of somewhat related. Now, the third part of Dalton's atomic theory is really just Antoine Lavoisier's law from the last slide, talking about definite proportions, that when you have different ratios of different elements involved to make a compound, they are just different compounds. As long as the ratio of the element stays the same, how much of it you have, well, let me go back just a second. I want to say something that's not true. As long as the formula of your compound is not changing, like it's that particular compound, regardless of kind of how you made it or what you made it from. Like if you have two hydrogens and one oxygen and combine them all together to make one molecule of water with two hydrogens and an oxygen, it's always water. Doesn't really matter what you started with, whether it was the two hydrogens and one oxygen or different ratios. If the end product has the same actual formula, it's the same compound. But as soon as you alter that ratio of elements, you do get other compounds, and that's a big deal because then those are going to have different properties like we already mentioned. Now, the other part of this, and this is the bottom part, is that when chemical reactions occur, the only thing that happens is how we change how the atoms interact with each other. We don't actually change the individual atoms themselves. And this means that like the ratio of different atoms of the different elements that are combining will likely change for the reactants that we start with versus the products that we form. But we don't actually change which elements are present. And this is important. Like for chemical reactions, like if you start with 5 atoms of carbon at the beginning of the reaction, you're going to have 5 atoms of carbon at the end for a chemical reaction. We will introduce, like I said, nuclear decay reactions before we kind of wrap up Chapter 2, really what we consider Chapter 2 content, and getting into Chapter 3 later. And when we look at that, then we have the potential to change like element identity. But for chemical reactions, that never happens. Chemical reactions, that's really kind of just this statement is really just the law of conservation of mass for chemical reactions. So really, like I said, the kind of just Dalton's atomic theory, it's really just kind of putting together all the ideas that everyone else has had. And saying that basically the building block particles here are atoms and kind of linking how that relates to everything else involved in those different laws that other people had kind of already talked about. Now, in terms of the atoms themselves, like I said, kind of the next thought process is, well, how do we break down atoms further? So we're going to take a look kind of at now getting into maybe within the last like 100 to 130 years or so of history of kind of what we've started to understand a little bit better. In terms of what particles actually exist within atoms themselves, and talking about kind of what's important about them. And so the first particle or kind of component of an atom to be discovered, we now call the electron. It was discovered by J.J. Thomson doing what was called a cathode ray tube experiment, which is basically taking one of these, this is a vacuum tube. So basically you have a gas here under vacuum, and you can pass an electric current through it. And by passing electric current, you can actually cause an excitation that can cause these electrons to be removed from some atoms. And so this little beam that you actually see is electrons. And by taking a magnet close to them, you can actually see them get deflected, which indicates that they have some kind of charge to them. And so they do have an electric charge. We now know today, or at least we can reference this as a negative charge based on how it interacts with magnetic fields and how we kind of define all of those things these days. And so we have these what we call negatively charged electrons that were kind of the first particle that we really discovered. Now, we understood that this particle existed, but we didn't really have a good feel for like how big it was. And like I listed here, like we were able to get a charge to mass ratio based on how deflected these particles got by magnetic fields, doing some reasonably intense physics calculations. But we didn't really know what is the actual size of these electrons, because we already knew atoms that by this point in time, atoms are very tiny. We kind of understood the existence of atoms in a way that we could use that to do calculations for chemical reactions. But we wanted more information, right? So we found this charge to mass ratio that I gave here, this 1.759 times 10 to the 8th coulombs per gram. Unit-wise, the C coulomb, this is a new unit that we haven't seen yet. It does stand for kind of like chemical charge, and its unit breaks down to like amperes per second, which is, again, a little bit, we don't use amperes very much, so we don't see it that much, but a coulomb, like, probably the most important thing is just realizing that it measures how much charge there is. The more coulombs you have, really like the more electrons or charged particles you typically have in what you're measuring. But what's important is we don't know the actual charge of a single electron, nor do we know the actual mass of a single electron, which is probably more useful to helping to understand atomic structure. So experimentally, kind of the next kind of process here, and again, I'm kind of just going through this history to get us to where our models of our atoms kind of came from. The next experiment, which is actually for the time a really ingeniously designed one by Robert Millikan, it was designed to basically figure out like what is the mass of an electron, and the way it did this was really cool. He would take basically some oil droplets that he could spray into kind of it looks like a glorified box. It's obviously much more intense than that. But inside this box, there was 2 brass plates that he could electrically charge with a positive or negative charge. And what he did is he put a little tiny hole in the top plate. And he put negative charge on the bottom, positive charge on top. And what would happen is these droplets would fall down through this little hole. And so there's one little spot that is basically these droplets are falling through. And through basically the side of the box, he used what basically X-rays. It's a form, basically, the easiest way to think about it right now is it's an energy source that if he hit these oil droplets with that energy source, it could cause those droplets to become charged negatively. And when they became negatively charged, what he noticed is that these negatively charged droplets would then get suspended because they'd be repelled by the negative charge at the bottom. And so he could actually observe these little oil droplets being suspended in midair, and based on the size of the droplet and how high it was suspended, he could make estimations about the mass of the droplets and the actual charge that was involved. And so, like, this is a, for the time, again, this is like early 1900s, this is like an ingeniously designed experiment. And what he found in terms of kind of the takeaway from all of this, he found that the charge of the droplets was always an exact multiple of 1.602 times 10 to the minus 19 coulombs. And so what he proposed is that must be then the charge of an electron. And what comes from that is if this is now the charge of the electron, J.J. Thomson in his original kind of discovery of electrons had figured out a charge to mass ratio. And again, that's just to point out the units of coulombs. If we knew the charge to mass ratio from Thomson's experiment and the charge of the electron here from Millikan's, now we can find the mass of an electron, which we now know is about 9.109 times 10 to the minus 28 grams, or minus 31st kilograms, depending on which unit you want to use, which obviously is incredibly tiny. And it turns out when we compare this to the mass of the other particles in an atom, this is really, really small, even still. And so when we see like the masses on the periodic table for elements, turns out the mass of the electrons almost doesn't even matter to that. It doesn't contribute enough to really make a big difference in the mass of most atoms. And that's kind of one of the big takeaways that, like I said, I kind of wanted to build our way to, that we'll kind of be putting everything together to here in a moment. Now, the next piece of this is scientists at this point, like after Thomson and Millikan's experiments, they understand that we have these negatively charged electrons in all of our atoms, but that also must mean there must be some sort of positive charge to kind of balance it out, right? Because not all atoms are negatively charged. We knew this at this point in time, so there had to be positive charge also, but there was a whole bunch of ideas in terms of where the positive charge was, how it behaved, and kind of what our atoms looked like. And the first kind of model, the atom, which is now kind of more referred to almost like a plum pudding model, looking back, it involved basically our negative charged particles that we knew were particles, and a positively charged kind of almost like it got referred to often as a nebulous, but it was almost, you can think of it as like a pudding. It was kind of like this charged, pudding of positive charge that kind of held all the negatively charged electrons inside of it, and that was what our atoms looked like. And we didn't really have anything else to go off of besides just the fact we knew there was these negative charge, or were the negatively charged particles. So we didn't have anything to really disprove this model. But thankfully, once scientists come up with ideas like this, remember at the start of the semester we talked about things like the scientific method also. Once you have kind of like an idea about how something is or why something is the way it is, you design experiments to test that idea and see how accurate it is. And so that's what people did. And people designed a test to try and basically figure out, like, can we detect this positively charged nebulous, or will we see something completely unexpected that will point us in a different direction? And so the next part of kind of talking about atomic structure is really about trying to find where our positive charge is. And this was the major breakthrough here is often credited to Rutherford with the gold foil experiment that he did. That I'm going to kind of briefly show and kind of explain here. But basically what Rutherford did is he bombarded gold foil with what's called alpha particles, which, again, we'll talk more about this when we see nuclear kind of reactions here in kind of the next lecture. But the most important part is these alpha particles are really just kind of like big positive charge particles for right now. And maybe big is a slight misnomer, but they are just positively charged particles. So what he would do is he took a little thin strip of gold foil and he just shot these little positively charged particles at it. And he just wanted to see, like, do these positively charged particles, do they, go through the foil? Do they get deflected really badly from the foil? Do they get absorbed by the foil? Like, what happens with them? Because ideally from that plum pudding model that I showed in that last slide, if the positive charge is pretty evenly spread all throughout the atom, if you shoot a bunch of alpha particles at it, they should all just more or less pass straight through. They're not hitting any big pockets of positive charge, so the alpha particles shouldn't really get deflected, and your beam of alpha particles should basically just travel right through this thin gold foil. But what actually ended up happening is not that. What he observed when he did this experiment is that most alpha particles did pass straight through undeflected, but a noticeable enough number of particles got deflected at really large angles, which could only happen if there's large pockets of positive charge somewhere inside the atom. And so this is kind of a quick look at the experiment here. You can see the beam of alpha particles being shot through the gold foil. Most of the alpha particles do still come straight through, but we were seeing some of them get deflected at really big angles, which again only happens if there's a big pocket of positive charge. So Rutherford's kind of explanation for why this would happen to kind of update our model of the atom is that our atoms are mostly empty space with kind of the electron particles floating on the outside, and that most of our positive charge was contained in something called a nucleus. So we kind of like almost imaged it like what you see over here. We have, if you imagine, and again, this is just kind of at the time, like a circular looking atom like this, or a spherical looking atom if we're thinking in 3 dimensions. We have a nucleus of positive charge at the middle. The rest of it's relatively empty space, other than maybe the negative charged electrons kind of moving around the outside, so that when we shoot our positively charged alpha particles, as long as they're going at a high enough speed, they're just going to pass through the empty space most of the time, but occasionally they're going to hit this pocket of positive charge at the nucleus, and that's when we see kind of deflections, or maybe even really big deflections if it hits it pretty close to head on, which if we had just that kind of, if the plum pudding model was correct, we wouldn't see that. And so this was kind of a pretty big breakthrough at the time for improving kind of our understanding of the atom. Gave us what we can refer to, if you want, as just the Rutherford model. We have a positively charged nucleus at the center, negatively charged electrons kind of on the outside being held in by that positive charge. But the other big takeaway is that most of the atom itself is actually empty space. And that's even still true, kind of our current model of the atom today. Most of the atom, in terms of the actual space that we consider it to occupy, is empty space. Most of the mass, however, is all going to be in the little tiny nucleus at the center of these atoms. And that's kind of the next piece that we're going to get into. So that was kind of a lot of history, a lot of background. I'm not one to really test over a lot of just like specifically historical pieces of information. So kind of to summarize a lot of this into what do we want to take away? What we want to take away is what are the components of the atom? And from that kind of Rutherford experiment, one of the other things we kind of realize is that there's more than just a positively charged particle that's going to exist to kind of balance charge. If all of our positive charge is in the nucleus, if all we did was take a whole bunch of positive charges and try to cluster them together, they're just going to repel each other, not going to hold each other together very well. And so we actually have a third particle that we call a neutron that's going to have a neutral charge. And the goal, and basically the purpose of these neutrons, is to hold all the positively charged protons, which is what we call our positive particles in this case, together. So our nucleus, where all the positive charge is made of both protons and neutrons, with the neutrons kind of like almost serving as like a glue to hold the protons together. And then our negatively charged electrons kind of moving around the outside. And again, I'll have kind of another visual of this in a moment as well, with kind of a slightly more modern theory that isn't quite to where we are today, but kind of another description or way to think about these things. But what we see here, a couple quick things to compare: masses, protons and neutrons. These masses are still really tiny, right? These are still incredibly small masses, but they are much bigger than the mass of electrons. So when we see masses for elements, it's pretty much just the protons and neutrons really being considered for the most part, because the electron masses are so tiny in comparison. We see the charges over here as well in coulombs, right? Electrons and protons, same exact numerical charge, just different sign. The neutron then is kind of like it sounds, the neutral particle of the bunch. Now, putting a lot of this together and relating things back to now the periodic table and kind of what are some of the applications of this information. We want to understand like what are atomic numbers and kind of some terminology that goes with these things. So remember, Dalton originally proposed that elements had different masses. We've kind of updated that now in today's age to that our different elements contain different number of these positively charged protons, and we refer to that number of protons that an element has as the atomic number. You will also see atomic number symbolized by either a lowercase or sometimes a capital Z, which will look strange because the next thing I'm going to talk about is the mass number, which will be A, and again, I don't know who chose the letter abbreviations, it's just kind of the way it is. So Z is our abbreviation here for atomic number, and really if you're looking at the periodic table, if you look at oxygen, it's usually got like a number either like at the top center or maybe top right corner of the little box for oxygen, and that number is 8 on every single periodic table, and that's because every atom of oxygen always has 8 protons. If you have a different number of protons, like if you had 7 or 9, you're no longer oxygen, you're the other elements that are next to it in the periodic table. Like if it was 7, it'd be nitrogen. If it was 9, it'd be fluorine instead. And along with kind of atomic number, something else that's useful to talk about is something called a mass number. And this is what they do use a capital A for. Again, why they chose Z and A the way they did for these, I don't know. It's just kind of the notation that's existed for a long time. But the mass number, all it really is the sum of all the protons and neutrons in an atom. So remember we said most of the mass is just protons and neutrons, so the mass number is just the sum of the protons and neutrons. And it turns out this is the part of Dalton's theory that wasn't completely correct. We can have what we call isotopes, which are atoms of the same element, so they have the same number of protons, but they actually have different numbers of neutrons, which means their mass will be slightly different. And so, for instance, in the case of hydrogen, even hydrogen, the smallest element, has 3 isotopes, what we call protium, deuterium, and tritium. The protium is just a mass number of 1. It has a single proton. Deuterium will have a proton and a neutron, so a mass number of 2. And tritium, which has a mass number of 3 because it's 1 proton and 2 neutrons. And here's just kind of a visual comparison of these. And it turns out for hydrogen, protium is like the isotope that is by far the most common in nature. Deuterium is considerably more rare, and tritium is extremely rare just because it's not nearly as stable. And it turns out this one's actually radioactive and will decay reasonably quickly into some of these other isotopes. Now, notation. This is important because we're going to see this a lot, not just in this chapter, but as we talk about like the nuclear decay reactions kind of next time, and really just something to kind of keep in mind a lot of the time in terms of like notations for like mass numbers, atomic numbers, things of that nature. You will sometimes see things written out, like carbon-12 or carbon-14. The number, if you see something written out like this, is the mass number that's being given. And the common notation is going to usually look like this. It's going to be the element symbol. The upper left kind of superscript is going to be the mass number. And then you often will have a lower left kind of subscript, which is going to be your atomic number. And you will sometimes see that this atomic number part gets left off. Because if you know the element symbol, you actually already know how many protons it has, so you might not see the atomic number always given. But this is kind of the general common notation. And so here, if I see something like this, I have 12C and then the 6 kind of in the subscript. What this symbol is telling me is that I'm looking at carbon, and this carbon has 6 protons and has a mass number of 12. Well, if it has 6 protons and a mass number of 12, that means it must have 6 neutrons to get that mass number. Likewise, if I have carbon-14, since it's still carbon, it still has 6 protons, but my mass number is now 14, which means I have 8 neutrons to get to that mass number. Carbon-12 is the most common, but carbon-14 is a radioactive isotope of it that can be used for some practical applications, things like radioactive dating and other things that will come up at different points kind of through the Gen Chem sequence. Now, the other thing I will note here, if there's no charges kind of indicated, we can assume that it has like the same number of electrons as protons. That's what we see for kind of just individual atoms normally. As we get into nuclear decay reactions, like I said in the next lecture, we will see this notation a lot. But in the nuclear decay reactions, we really are only looking at the nucleus. We kind of don't even consider the electrons because for nuclear reactions, the electrons don't matter, which is kind of the total opposite of everything for chemistry that we're going to see for really the rest of kind of all chemistry classes you probably ever take. Chemistry is really all about what the electrons do. And so we have ways to notate kind of what's going on at the nucleus, but it's really going to be these electrons that actually do all the real chemistry for most reactions and compounds and everything that we're going to encounter. All right, so after kind of all this background information, there are some kind of calculational things that I want to kind of introduce and have people kind of be familiar with as we start moving towards Chapter 3 and are going to start doing calculations regarding reactions too as well. And the first of which is going to deal with atomic masses. So when we talk about atoms, since they're so small, talking about their masses can be kind of awkward to talk about in terms of grams. And so we have a couple different ways of dealing with this. One is that we can talk about their mass in a unit called AMU. It's defined as an atomic mass unit, where 1 AMU is defined as exactly 1/12 the mass of one carbon-12 atom. Carbon-12 is kind of used as the standard for a lot of these things for where they got their masses from. And when you're looking at the periodic table, like in terms of like the numbers you see in the periodic table, that's the mass in AMU of an individual atom of that element. Now we're going to see there's another way to consider that number as well. And also, in addition, when we're looking at the periodic table and kind of the masses and the numbers usually at the bottom of the boxes for all the different elements, most of those numbers aren't whole numbers. And that's because atomic mass is a weighted average of all of the naturally occurring isotopes of that particular element. Right? So in the case of hydrogen, we said there was 3 different isotopes. Most of them are all that protium that had a mass number of 1, and then a couple with the mass number of 2 for the deuterium, and very, very few of the tritium with the mass number of 3. And that's why when you look at a periodic table, like hydrogen's atomic mass is roughly about 1.008 AMU. So on average, that's the mass of a hydrogen, and it takes into account kind of how abundant each of those isotopes are. Right? So here's kind of a common notation that you'll see in the periodic table: atomic number on top, the symbol of the element, atomic mass on the bottom. And again, sometimes these will be very close to whole numbers like carbon, or hydrogen even for that example. But the reason they're not exactly whole numbers is because there are multiple possible isotopes of those elements that occur. And since the isotopes themselves have different masses, we do take this what we call weighted average to figure this out. So I think the best way to explain weighted average is to just kind of show an example of using it. And I'll do this for really calculating the atomic mass of chlorine as an example. And so how this works, in order to calculate the atomic mass of something, what you need to know is how many isotopes there are. And for every isotope of that element, you need to know what is the mass of each isotope and what is the percent abundance. So roughly, like, if you have, 100 particles of that particular element, how many are each of the different isotopes? And you'll see the percents are actually more exact than just having only 100. But here for chlorine, there's 2 major isotopes. We have chlorine 35, so it's a mass number of 35. Its percent abundance is about 75.77%. And our other isotope is chlorine 37 with an abundance of about 24.23%. So that means 75.77% of all chlorine atoms in nature are chlorine 35, and the remaining 24.23% are all chlorine 37. And those are the only 2 really naturally occurring isotopes of chlorine. And another thing I want to point out, the mass of the individual isotopes, usually this mass is always going to be just barely less than what the mass number is. So notice chlorine 35, the mass of that isotope 34.97, it's very close to 35. Chlorine 37, 36.97 is just below 37. That will always be the case for isotope masses. So just in case you ever actually run into an example problem where it wants you to calculate the mass of an isotope for a particular element, if it's like, well, the mass number of the isotope we want you to calculate is, 130, you should expect to get an actual mass that's just below 130. It's like 129.9 something probably. Now, setting up this calculation to use what we call that weighted average, basically what we're going to do is we're going to take this percent abundance and we're going to make it a decimal instead. So basically we're dividing it by 100 to make it a decimal. And then we're going to multiply it by the mass that particular isotope has. And we're going to do that for each isotope and then just add them all together. So the way this calculation looks is the atomic mass of chlorine should be equal to, here's our percent abundance of chlorine 35 as a decimal, multiplied by its mass in AMU. Notice I've given a few more digits here that we can look up. And then doing the same thing for chlorine 37, here's its percent abundance as a decimal, multiplied by its atomic mass. Again, I give a few more decimals on the atomic mass just to be a little more precise. And when I go to put all of this together, I can get kind of each of these products individually, and then I'm going to add them together. Now, one thing that can be a little bit annoying here is that we can be careful with sig figs, right? So multiplying these 2 things, like here's 4 significant digits in this number. This one actually has like 6 now, the way I've written it. And so I'm going to have 4 sig figs here in this number as I've multiplied them. Here I have 4 sig figs, 6 sig figs multiplied, so 4 sig figs in the product. But now when I go to add these 2 things together, if I know this one only to the hundredths place, this one to the thousandths, I'm going to round to this hundredths place when I add it all up. And so that's how I get, adding all of this together, roughly about 35.46 AMU for chlorine. And you'll see in the periodic table it's actually about 35.45, so it's very close to this. There's some differences in percent abundances and some other things that go on there that lead to that. But this is kind of how the calculation works. And the nice thing is it doesn't matter how many isotopes you have. You could have 5 isotopes. It works the same way. It's just what's the percent abundance as a decimal, multiply it by the mass of that particular isotope, do that for every single isotope you have, and just add those different products together, add them all up, and that should be your atomic mass. Now, one other thing I will note, just that you can always check to make sure that you have an answer that kind of makes sense. It's something I always like to harp on all the time. I'll probably remind people of this in the actual lecture too. Here I have chlorine-35 and chlorine-37. If these are the only two isotopes I have, my actual atomic mass, since it's really an average, even though it's a weighted one, should be between these two, right? So I'm not going to get, like, if I have, mass numbers of 35 and 37 for my isotopes, I'm not going to get an atomic mass at the end of this of like 22. If I do, I've done something horribly wrong with the math that I'm trying to put together. And so you can kind of keep that in mind. We do expect an atomic mass in between these two things. And notice it's closer to the mass number of 35 because it had the higher abundance. So you can kind of hopefully look at those and kind of reason through some of the results that you actually end up seeing out of that. Now, one last piece I'm going to kind of add to this to kind of wrap up for this content for right now is introducing something called Avogadro's number and the idea of something called molar mass. So Avogadro's number, we mentioned it actually very, very briefly earlier this semester. It's what's used to represent when you have a mole of something. So remember we said if you have a mole of something, it's kind of you're assigning kind of a quantity of something that you have. It works kind of like a dozen. People are familiar, like if you have a dozen of something, you have 12 of that thing. Well, if you have a mole of something, you have just 6.022 times 10 to the 23rd of that thing. And this 6.022 times 10 to the 23rd is Avogadro's number. Now, the reason I bring this up is because this is actually really useful to us. Remember, atoms have really small masses. So before we were calculating the atomic mass in units of AMU, but if you're in a lab, there's no balances that we're ever going to use while we're in the lab that measures in AMU. That's just too small of a quantity for us to really be working with in our hands, like in the lab, for instance. We're usually measuring things probably in units of grams. So what's useful for us is to talk about masses of things in what we call molar mass. And what we can do, it turns out the numbers on the periodic table, the reason this was chosen as Avogadro's number is by using this as what we quantify a mole. This gives us kind of a relationship between AMU and grams, so that the numbers that we see in the periodic table for atomic mass, they can have units of AMU, or they can actually be the mass in grams if we have 1 mole of that substance. The numbers are actually the same, and that's why the mole was chosen to be kind of what it is. So numerically, molar mass for an element will be the exact same as the atomic mass. It'll just have units of grams per mole instead of AMU, but units of grams per mole are actually much more useful to us in the calculations we're going to be doing for pretty much the rest of chemistry than trying to work with things in AMU, which is just a not practical unit to work with in a lab setting. All right, so I'm going to end kind of my pre-lecture stuff here. I think this is plenty long already, unfortunately. And again, we're going to summarize probably in lecture what are the major takeaways, and this atomic mass and molar mass part, we're going to look at calculations and kind of applications of this, because that's kind of the really big important takeaway from a lot of this information, understanding kind of what's our general picture of the atom right now, and being able to adapt and expand and kind of like take away things like atomic mass and understanding how to notate like mass numbers, atomic numbers, and things of that sort. So those will be kind of the things that we'll be looking at in lecture. But that's it for this time. I'll have another video up probably in a little while that'll be taking a look at nuclear decay reactions that we'll probably be getting into in the next week as well.